تمام. صباح الخير يا جماعة. Good morning everyone. Sorry for the delay, but now we see that the hall is complete almost. So today we have a very exciting collection of sessions, and we are going to start with very wonderful session about quantum systems and information. Yesterday we have seen the challenges of the hackathon, different talks about the education and the ecosystem. We have seen from our professors the diversity of researches in Egypt, but also in Africa in general. Today we are going to start our session with Professor Ahmed Al-Mahdi. He is the Dean of the ITCS School at Nile University. He joined Nile University in February 2023. He got his master and his bachelor and the master from Alexandria University and a PhD from Manchester University, UK. Coming from a computer systems background, Professor Al-Mahdi is now exploring making quantum computing usable in practice. His group is exploring quantum AI, dealing with quantum noise, developing self-healing quantum memories, and doing practical quantum communications. And he has very strong collaborations with different and many international universities. Welcome, Dr. Ahmed.
طيب أنا يعني I will try to be brief. طبعا I am so happy. Sorry, I have to talk in English. Yeah, all right. So I'm really so happy and honored to be with you here. And actually, so as Dr. Taha kindly presented me, so I'm actually more into systems guy. I'm coming from computing systems background, computer architecture, parallel computing systems, and so on. And of course, I am so fascinated about quantum computer because of like the acceleration, the speed, the potential. And again, I like to make things happen. So I am more into the, let's say, the how to make the systems work. So my focus today on the talk is about the error mitigation. And as you can see from the agenda or the outline, I'm just going to give you a brief introduction to quantum systems from the way I see it. It's not really high level. I like to go deep a little bit. And then I'm going to talk about error mitigation. And basically, this work has been done by our group, actually. And yes, I think already I've been introduced. So I'd like to introduce my team. So I'm really so proud to have all these people with me, so honored. I think Professor Salem Higazi might join today, I'm not sure yet. And as you can see, I have, actually many doctors and professors, which I'm really so happy about that, and many master students. And actually, I'm very lucky also to have collaboration from universities from Tokyo in Japan and the Gulf and many other places. And I think working alone, of course, is not the message here. It's really the teamwork. Yeah. So I'm also have undergraduate and so on. All right. So maybe I'd like to start with just basic concept in quantum computing because again, I am systems guy and I like to see the things from the low level a little bit. So let's start by a very simple question. What's a quantum, right? So does anyone know what's a quantum? I say quantum computer, quantum mechanics. What is a quantum, right? So so maybe just to save time, it really goes back to Albert Einstein. And maybe I'd like to show you some live demo. I hope it works. Some very interesting experiment that has been done in like maybe more than 100 years ago, very long time. So I don't know if you've seen this before. This is called the photoelectric effect. Have you seen this before? Okay, good. So anyway, so what they did in the past, they have this kind of very interesting experiment where you can change here the color. There is some light here, okay? And you have some material here, right? In this case, it's like sodium, whatever. And then you can increase the intensity of the light. So what happens here is that this light is like energy, right? And when you kind of turn on the light like that, this energy somehow excites the atom on the surface. And if the atom is excited and so on, electron can leave the surface and move. And then you have electricity. All right. So if I increase the intensity of the light, so this means that now we have more energy, right? But nothing happens. There is no electron that moves. Nothing happens. All right. So maybe the energy is not good enough. All right. However, if you change the color of the light, see what happens. Electrons start to flow. So this puzzled scientist, why? This is for the same intensity setting, same power setting. Why changing the color makes, yeah, you see, going into like high frequency, things go crazy and electricity goes like very fast, right? So the question is, why? Do you know why?
Shorter wavelengths carry more energy.
Sorry?
When I decrease the wavelength, so I go up to UV, the light carries more energy, so it can knock off the energy.
Yes, but if this is the case, right? So if I'm here, let's say, all right, and now I increase the energy, maybe I can put here infinity if you like put some light bulb like that with like megawatt. It's still not good enough. So this is much big energy, right? So no, it doesn't work.
I think because the emission is depending on the frequency, not
Yeah.
depending on the density.
Yes, but if this is the case again, I can make this my megawatt bulb, right? I can use the dam of Aswan to turn on one light bulb. So you can use the sun, for instance, yeah? So you can have much energy as you like, right? So this was really a big puzzle, but yeah, maybe one last.
Because the energy of the wavelengths must be some greater than the barrier or the threshold of the material itself.
No, again, because the energy, no. Just to keep it very simple, what Einstein said, let's go back to the presentation. Yeah, so Einstein just said, actually, light is just a form of discrete units of energy. It's like having packets of energy. 1 packet, 2 packet, 3 packet. So if you put like million packet, it's okay, but everyone has got fixed amount of energy. So you can think about it as these units of light or energy, they call it photons. So it's like a particle. It is a particle in a way, right? But this strange particle, it's got like fixed units of energy, 1, 2, 3, and so on. And this explains what happens. And actually, he got his Nobel Prize because of that, just to understand that it's quantized. The light is composed of photons, and these photons has got some energy. And this energy is actually depending on the frequency of the light. So energy equal H, which is the Planck's constant, and V is the frequency of the light. So when you increase the color, or the color when it becomes like magenta or so on, it's more energy. So it's like you have packets, and every packet has got high energy. Now this packet goes to the electron, and then the electron energizes and leave. So you can think again as like you have some ping pong balls and you throw it to some atom. So if you keep throwing with very high rate, it doesn't matter. What happens is every ball has got fixed amount of energy. So if this energy is not big enough to get the electron out, it will make nothing. All right? And this actually changes many things. And the word quanta means like units, 1 unit, right? Quanta. And of course, quanta and quantum. So quantum is the plural of quanta and so on. Quantum is 1 and quanta is plural. All right. Now, second thing. Now, this kind of strange world where you have these packets of energy or photons and so on. So how do they behave? They don't behave like the mechanical system at all. All right. So how do they behave? They actually different. So let's go back to the mechanics. What is mechanics? I think you all studied in school or university that this famous, like how to say, Newton laws of motion. You have a mass like that. Like this is the apple, let's say, and this mass like goes down. And if you label this axis as x, and then you can work out according to the mechanics that there is some force pushing this down, and this force is proportional to the mass, right? And g is the gravity, acceleration due to gravity. But what happens in the end is that you compute the state of the apple, right? So the state of the apple here is like where it is at certain time. So at time 0, maybe it's somewhere. Now at time 1, where would that be? Right, so if you put here t0, according to this equation, it will be like 0. So we say like this part is 0. So if I change t here to 1, whatever, so you start to move on, right? And your location is here. So this equation, you can derive it using the mechanics that we all studied in school, right? So this is classical mechanics. Now, what happened with the quantum mechanics? Things are so crazy, and I always like to go back, very much back in time, to 1804. That's a very long way ago, right? And at that time, there is a very famous, I think, British scientist called Thomas Young. And he did his very famous experiment called the double slit experiment. And this was very strange. So actually, he put some laser, or some, not laser, at that time was the sun. So he made the box, and they got the light from the sun. There's two slits on the box, and in the back of the box, he gets some pattern like that. So yeah, so this was strange. Why? Why it's kind of dashed pattern? What happens? All right, this was very strange phenomena. Why? What happens? So anyway, so yeah, maybe because of time now, but anyway, I can give you the link. You can play with that. So somehow you can explain this pattern as if the light behaved like a wave. All right, maybe quickly I'll show it to you, and maybe I'll skip at the end because this might be interesting. All right, so actually all the animation I'm showing you, actually they are developed by a scientist, and actually I can't remember the name of the guy now, it's in the slides, but he's also a Nobel laureate. All right, so yeah, so anyway, so yeah, as you can see here, if I just play, you can see that there is a wave here. There's like a water, and there's like wave front moving, and the two slits are here, and somehow they are interfacing, interfering, sorry, together like that, you see, and they're making this kind of interesting patterns that somehow exactly looks like the pattern that he got in this 200 years experiment. So this puzzled scientists, and they start to think like, is light a wave? Is it particle? Is what? This was a long time ago. But when Einstein came and said just light is just photons, this was very interesting. So how can you explain this interference pattern? All right, so okay, now comes Schrödinger. Schrödinger was asked a question like that in maybe, yeah, it's about more than 100 years ago. And I think, yeah, it's exactly 100 years. And that's why this year is the year of quantum, as you all know. Right, so actually he's been, yeah, asked like, if then somehow the particle behave as a wave, then there should be some wave dynamics there. There's some wave equation. How can this wave behave? How can it be generated? What happens after t? So like when we talked about the quantum mechanics, we said, give me the position of the apple at time t. So now give me the wave at time t. So how to do that? So he came with a very famous equation that actually is in tombstone, which is the Schrödinger equation. And it's a long story, of course, but you can see that this symbol represents the wave, and this symbol represents the energy somehow. So somehow the system or the wave evolves, yeah, depending on the amount of energy you have. I know this is a bit complicated, but just to make it simple, I'll show you another demo now. But before showing you this demo, the essence here of a wave is very strange. It tells you like, all right, so don't worry about where is the photon or why the interference happened or everything. Just think about the photon as a wave, all right? And this wave somehow explains the state of the system. And when you look, it disappears. Yeah, so anyway, maybe I talked a lot here, but let me show you a demo just to understand what I'm saying. If you look at this nice animation here, all right, okay. So what's that? Let's pause here. Okay, so we have here, this is a source that releases some photon, as you can see here. And then at a certain time, maybe I can start from the beginning, it will be easier. Let's reset, okay. And actually, let's put the two slits again, and let's, yeah, make them closer slightly like that. And let's start by just one step at a time, like that. Now, what happens here? as you can see, this kind of magenta thing looks like a wave, right? There is something moving here. Now, every pixel here have got a color. This color is we call the amplitude of the wave. All right? Now, yeah, just to keep it maybe, sorry for that, but maybe it's a little bit complex. This number here, it's not a real number. It's a complex number. So that's why they call it actually a complex amplitude. Now, this is very strange. Yeah, nobody understands why it's complex, but it works. All right. So you can think about the wave as something like that, but these points are actually two-dimensional. There is a color, and there is other color maybe, or whatever representation you like, which is the phase or whatever. Now, what it tells you here is that this is the state. It's not like I'm telling you the apple is here at that time. I'm telling you at this moment of time, this is the wave. So where is the particle? Do you know? Where is the particle? Where is the photon? So Max Born told you that if you take the amplitude of every point here and square it, you get a number. This number is actually the probability that it will be here. So this basically gives you probability distribution of where to find the particle. So if you don't look, it will be like that. If you look, it will be only one pixel here, depending on the probability and your luck, and everything else will be black. Now, to explain what happened in the two-state experiment, you can see this is what happened here. So at this moment of time, it says that there is a chance to find the photon here, to find the photon here, to find here, to find here, to find here. But as you can see now, it's like saying the photon or the wave is here and there, right? There is a wave here and here. So if you don't look, there is a wave here, amplitude here, amplitude there. So it's like saying the photon is actually here and there and there and there and there and there and there, all this position at the same time. And I think this kind of strange phenomena, I think they call it superposition, which means that it's no longer this apple is in there, right? Actually, it's kind of all these places, but when you look, it will be only on one of them, right? So this is very strange, but this is how it works. Nobody understands why up to this moment, and there are many interpretations. Like there is a Copenhagen interpretation. There is, I can't remember the others, but the Copenhagen is the most famous one, and this is what I just explained to you. Now back to our example. Actually, I generated this pattern using YouTube video. If you get some hair like that, and you have a laser, and you put it like that to the hair, and look at the wall, you will find this pattern. So where is the wave equation here? So you can say like that, if this spot is red, the laser is here, right? So this means that I made an observation and the laser hit this space. When it's dark, this means that there is no photon here whatsoever. And when you turn the laser on, you have like billions and billions of photons flowing, right? So as if you're doing many, many observations. So you can tell there is nothing here, that the wave here is zero. The wave here is very high. Here is zero, and so on. And actually, we made this video. Not sure if it works, but yeah, I can give you the code as well. You can try it yourself. We just use some equation here. This is the wave function. And actually, maybe I can just go back. Yeah. So you can see here, now I have some particle. This is after like the slit, the division from the slit. And you can see when these two waves gets near each other, they start to interfere like that, you see. And actually, what we did here in this very simple code, we just run the solution for Schrödinger equation, which actually explains the state. So as you can see, every moment of time, the wave like moves and interfaces with itself and makes this very nice interference pattern. Okay. Of course, you know the Schrödinger cat. I'm not going to repeat that. And so on. So let's move on. So now, in order so this is like basic phenomena. And then, of course, when you look at the quantum mechanics, they tell you the state is the wave function. And the wave function is basically what I've shown you, the wave. But if we're working now with digital computers and so on, we like to have a notion of a qubit, right? A discrete state. It's not like everywhere. So maybe we can use, again, the two-state experiment to explain that maybe I will say that if the photon is up, this is location 0, so this is state 0. And if the photon is here, this is location 1. And now we mentioned that there's a complex number here. Maybe we can represent this complex number as just a very simple wave with the amplitude and the phase like that. And then you can say that the state at this moment is basically these two complex numbers, the complex amplitude here and there. And usually in quantum mechanics, this is what we do. We say now we have two numbers, so a nice way to represent these two numbers is just using a vector, right? And then you have the Dirac notation, so so you can represent it like that. This is normal vector, and then 1, 0 is like that, and so on. So you have some linear algebra to represent your state. So a vector becomes your state. Right, and of course the interference can be explained by just adding these two numbers, and everything works. And if you work out the equation, this is like what I did, you actually can see this is the interference pattern, like this is the x-axis here, and the y-axis is like the probability of finding the photon. So you can see it's very similar to what you get from the experiment. All right, so now if you build the quantum computer, we start with the qubit, as I mentioned. And of course, you've seen the block sphere. I'm sure you've seen it many times. But what's interesting here is that the state for one single qubit is basically any point on this three-dimension sphere. And this is crazy, because this means that a single qubit can represent, like in theory, infinite values. And this is where the quantum information kicks in. Right, of course, you know about the quantum mechanics. I don't need to get into that now, but it's just, let's, because of the time. And I just want to quickly, just before going into the error mitigation and so on, to show you, like, actually, this is like some simple experiment I made just to understand how quantum computer works. And basically here, I tried to say, like, I want to detect the case if it's like a game. It's a very well-known algorithm called Deutsch-Jotze or whatever, but I just implemented it using very simple light interference. So I just like engineered a very simple system with 4 slits like that. And somehow, if I have 0 and 0 here, I made the interference to be like constructive. And somehow, if you look here, you will find some light. Anyway. And if you have like 2 different numbers, you get 0. You don't see light. So the whole puzzle here is like, I'll just give you some numbers. And if they are the same, you tell me they are the same. If like half of them are 0 and half of them was 1, you tell me that. So to do this quickly, you can just use a very simple interference like that, or you can do it even with 3D and shed the light like that and get the interference. Anyway, I'm just trying to show you that you can build many things with this crazy interference idea. Now, maybe I just to quickly just to give you some impression of this, the complexity here or the power of quantum computer. I know maybe you've seen this before, but just quickly, if you just have 1 qubit and you are just allowed to be on 0 or 1 or both, like, so you have like 3 possible combination, right? Now, if you have 2 qubit, what are the possibilities? If you just have like zeros and ones, like superposition between the possible changes. So you can say that I have 0, 0, right? I have 0, 1. I have 1, 0. I have 1, 1. Anything else? No? No. It can be 0, 0 and 0, 1. Anything else? All right. If you like math, you can work it out. If you have n qubit, you can actually represent 2 to the power of 2 to the power of n different states. And this, if you just use maybe 7 qubits, you can have a number which is larger than the number of atoms in the universe. Only with 7. So. All right. Anyway, now we move on from this kind of simple low-level representation into, again, to the quantum mechanics or quantum computing model. Of course, you've seen the circuit model, and basically you have some gates, and these gates, of course, operate. So you have states here, like you trace the circuit, so you start here with some input state, you do some operation like Hadamard, you get some new state, you have C0, you have another state, then you measure and you collapse and so on. Right. So yeah, this is the circuit model, and it's very famous. And of course, you know the gates. I'm not going to take time on that. And yeah, now we are getting more into quantum systems. So let's look about how quantum processor looks like. Usually, what you see here is typical quantum processor based on the superconducting technology. What you see here is basically like a fridge. So it's cooling. Yeah. So the processor is somewhere here inside this shield. And all of that is like cooling. Yeah. So, but let's go inside the quantum processor. What's in there? So actually, conceptually, it's so simple, right? You have some, of course, you have some classical processor, which is usually called like, maybe host or whatever. And then you have your quantum processing unit, which includes some control processor and the actual quantum hardware. So the actual quantum hardware, you have the qubits, which everyone can be 0, 1, or crazy 0 and 1, and so on. And these links actually tells you that you can do like 2 qubit operation like CNOT. So you can do CNOT between this and this, but not those. And the whole idea is that every cycle you execute some gates. You say, this is Hadamard, this 2 CNOT, this one maybe not, and so on. And then you can read if you like or not. So it turns out to be like it's kind of sequence, like standard, like in the classical world, like you have some fetch, execute, fetch, execute. It's like that. But here it's like execute, read out, execute, read out, execute, read out. So it's kind of sequential execution. Right, so this is how it looks like. Of course, there are many technologies, not just superconductors, there are trapped ions, there are photonics, and we are actually at Nile University very much interested in photonics because we do believe that it's much cheaper to implement, and usually you don't require the cooling that is so expensive. But for us as computing engineers or scientists or people interested in building computers, of course, you also should be interested on the stack, like the system stack. Like in classical, we have transistors, assembly, high-level language, and so on. In quantum computer, you have different things. We have, of course, very low-level language, and we have lots of things here in how to compile, how to do error correction, how to mitigate noise, optimize, and so on. So most of the work nowadays actually happens here for the software guys, how to make the computing reliable. Because up to this moment, of course, there is lots of hype, and of course, we all like quantum computing, but usually people are still skeptical, right? So can it really do something? Of course it can, or we believe that, but up to this moment, we still don't have a very concrete things. We have maybe some toy examples and so on with some interesting problems. Yeah, so it's all about the noise. If we can decrease the noise, if we can scale up the number of qubits, if we can build what's called the fault-tolerant quantum computer, that's what we're looking for now. So the current era of computing system, usually it's called the NISQ, according to John Prescott from Caltech, which is the noisy intermediate scale quantum computer. But now we're saying that we are entering the LISC, the logically intermediate scale quantum computer. So it's like logically fault tolerant, but the number of qubits is not very high. So now I think IBM is the leader now with like 1,000-ish qubit, and they plan to increase more. But recently, a few months ago, there was like new technology from Microsoft called Majorana, I haven't really studied it yet, but it's sophisticated, and they claim they can reach millions of qubits, but we're still waiting to see what's going to happen. So now this was like a quick introduction to quantum systems. I'm really sorry for taking most of the time, but now I'm just maybe give you some highlights about our research here in error mitigation. All right, so basically I'm going to highlight two things, right? So of course, the quantum system now are noisy. So this means that if you have some state, of course, it can change, and it will not last for a long time. It's so fragile, right? So basically, we did two things. The first is to characterize the noise, to find out how much noise is there, and usually this is called the state fidelity. All right, so let's tell you like more information about that. And if you're interested, you can find the paper here. It's open access actually, and thanks to the Egyptian STDF and the Egyptian Knowledge Bank, It's actually, they paid for that to make it free accessible, so you can access that. And yeah, so basically just to keep it simple, in order to tell how much noise you have in your circuit, yeah, it's so difficult process actually. You have to start with some circuit and do something called the tomographic measurement. All right, have you heard about tomography before? No, okay. So you can say that this is very expensive way to find, yeah, to characterize the error. So basically you have, if you have 1 qubit, you have to repeat or make 3 experiments. If you have 2 qubit, it's 3 to the power of 2, it's 9. It's exponential on the number of qubits. So you have to do exponential number of experiments. And from those experiments and measurement, you reconstruct the quantum state. And I think the world leader here is, I think it's called Jay Gambala from IBM. I think he's the guy who made this very efficient, or this step very efficient. And then you got the fidelity, right? So what we do in our research in our group was that this was actually back at that time in EJUST, in Egypt, Japan University of Science and Technology. So we proposed a very different approach using just classical machine learning, where we tried to train some network just to encode the circuit and give it to this network and try to predict the fidelity without doing this 3 to the power of n experiment. So this was very ambitious goal. And at that time, actually, the number of qubits was 5 qubits. This was 4 or 5 years ago, or slightly, maybe 3 years ago. Yeah. And actually, as you can see here, we started experimenting with thousands of circuits. Yeah. At that time, actually, the quantum processor access was for free at that time for this 5 qubit. So we made use of that. It took us maybe 1 or 2 months full time on a quantum processor. But in today's, yeah, it'd be so expensive to do. But at that time, it was so cheap. It was free, actually. Yeah. So what we did here is that we got a circuit, and we made some encoding. So as you can see, this is C naught. So it becomes here, yeah, just 5 from 5. This is C naught. This is RZ, rotate Z gate. This is another gate, the same, and then square root X. So we encode basically these circuits with numbers. And then in the quantum processor, we have this called the topology. This is the hardware. So this is qubit 0, qubit 1, qubit 2. And this edge means that you can do actually C naught, or 2 qubit gate on these two. So we modeled this here, right? So every link here we mentioned, 7 is nothing, 8 is C naught, and 6 C naught, but the other way around. So here, for instance, between 0 and 1, we have a C naught, so that's why we have the 8 here. Now between 1 and 2, we have C naught, but it's the other way, 1 and 2, so it's here, the second stage is 6. So anyway, so we encode this circuit with some matrix, and of course it can be a vector, let's flatten it out. And we started to make some machine learning model here. It's long details, I don't want to get into that, but just a standard convolution neural network. And what's interesting at the end is that we managed to estimate with really not bad accuracy this is the predicted fidelity, and this is the ground truth value. Of course, you can see there is some noise here. Ideally, it should be, along this line. And what's interesting, actually, we found some interesting noise in the quantum system. So you can see we're running some random systems here. The y-axis is the fidelity, or how good you are. 1 is perfect, of course. 0 is so bad. And we just randomly generate circuits. And you can see during this time, something odd happened. And there were much noise there. I think it's called maybe dynamic noise. I can't remember the name now, but this phenomena has been reported elsewhere. And what we did, we just did some pre-processing, and we tried to remove these kind of episodes where the noise was excessive. And interestingly, this is what we got. So this is before and after. So you can see now our prediction becomes much accurate, actually, after removing the noise. Anyway, so we tried that on 1, 3, and 5 qubits, and we showed that somehow the system really works. And actually, we run on some quantum benchmarks. This is a set of known circuits. And what's interesting is that yeah, this is the ground truth fidelity. This is what we got. It's really nice. And our correlation was 0.967 or 8, sorry, which is very nice. And this is what you get if you just use some simple heuristic. So I think it was really not bad. Now, the next thing we did was now we can somehow estimate the noise. So how to decrease that? And this is what's called the error mitigation, right? So yeah, so we actually, of course, this is a very big problem, but we focused only on very important sub-problem here, which is the C notes, right? Now, if you look at this circuit, for instance, if you have a circuit like that, like a simple, like 3-stage circuit like that, and you want to operate here the C naught between qubit 0 and qubit 2. Now, if in your hardware, on your quantum processor, you don't have like an edge or, yeah, so it's not possible to directly, it's like that. This is the back end here. So you can operate between 0 and 1 and 1 and 2, but I want 0 and 2. It's not possible. So what should we do? We have to swap. So we have to swap qubit 0 with 1. And this swap can actually be implemented by 3 C0 operations. So in order to implement this simple 3-stage circuit, now it became more deeper. Actually, it was 2 here. So now it become 5, depth 5. And the more you increase the number of gates and the depth of the circuit, the more noise you have. All right? So one simple idea was like, so why should I map 0 to physical qubit 0? If I just do simple mapping and change the order here, yeah, something like that. It should be very simple, right? So if I map just Q1 to 0, Q0 to 1, and 2 to 2, so it's just basically like swapping these two together, then you can do it directly, right? So now this is the problem. So as you can see, the choice of the initial mapping between the logical circuit and the physical is so important. So we ask this question: would it be possible to find out an initial mapping to decrease this number of C nodes? And actually, maybe here you have only one C naught, but you can imagine if you have a very big circuit with many C naughts, it becomes more difficult. And usually this problem, they call it routing problem, because it's like you'd like to connect 0 and 1, it's like moving some packet or so. It can be, yeah, there is some similarity between this one and the routing problem in networking. All right, so what we did, we actually used, again, classical or non-quantum machine learning. We used reinforcement learning to do that. There were lots of related work here, but basically they were not very general and basically used based on heuristics. So yeah, so we actually proposed a simple system based on reinforcement learning. Because a very simple way to do it, of course, is to try all possible combination, which is factorial n. But we used machine learning with reinforcement learning. I don't know if you've heard about reinforcement learning. It's so famous, using agent. And we formulated the problem as a learning problem with reinforcement learning. And we actually did that on 84,000 circuit. This is a lot, took a lot of time. And we, again, I don't want to take much time from you, but we started to only focus on the C notes, and we find a way to encode them and represent them in a matrix way. And we just use a standard reinforcement learning model. It's called the actor-critic neural network model, and train it on this data. And actually, interestingly, we managed to get very interesting results. These are standard set of benchmarks. And the column at the end is the improvement we got. So this is the number of logical C notes. And these are the new C notes we had to add for the swap using the state-of-the-art methods. And this is our approach. So yeah, most of the time we are actually better. And I think any improvement you make is significant. Yeah. And also, you can see here our representation here is actually simple. And for other systems here, the representation is somehow dependent on the number of C nodes, but ours is constant. And actually, our approach was much faster and scalable. Yeah. And I'm very proud that actually this work was cited by IBM, Quantum actually, and we're very proud of that. And we have very interesting citations now. So anyway, so I'm really sorry to take maybe more than the time allocated to me, but I just wanted to give you a hint about what's happening in the quantum, how to say, error mitigation quickly, and give you some background about how kind of quantum computer works in a very simple way, I hope. And the message, the take-home message here is that now, I think what we are moving for is this LISC, logical. Now we are like intermediate scale. The number of logical qubits that are fault tolerant are very few. And I think now the future is basically about this fault tolerant, and we want to make a good computer that it does not suffer from noise at all. And I think this is really a strong goal. And and I encourage, of course, people to consider working in this area. Yes. Thank you. Any questions? Sorry.
Any questions? Okay, so I have a question myself. So how do you see the future of error mitigation? How far we can reach with this? What would be the end game of the error mitigation? Like now we have the gross code from IBM, we had the surface code before, and of course with every type of code there is progress, but what will be the ultimate progress with the techniques or the extrapolation line?
Okay. So this is a good question. The answer is I don't know, of course. But to be honest, I think we shouldn't really only think about the frame of reference of mind where we consider the traditional error correcting code. Maybe there's something else. I know now we are working on people considering the variational quantum circuit, and variational quantum circuit somehow works, right? So maybe instead of just dealing with the error, maybe we can live with it and try to find something. I think this is kind of doable. But the other goal, of course, would be great. But to be honest, I don't know. Thank you.
Thanks very much. I think that I think the idea of live with the error and try to scale maybe that will might be the potential one.
Yes.
Thanks very much, Dr.
Thank you.
For us today. So the talk will be about building secure quantum communication systems. Dr. Salim Hijazi, as an associate professor in Cairo University and also Nile University, he received the bachelor degree with honors and also his diploma and master degrees in electronics and communication engineering from Cairo University in 2002, 2006, and 2011, respectively. And his PhD degree in quantum optics and quantum information in 2017 under a joint supervision scheme between Niles, the National Institute of Laser Enhanced Sciences, Cairo University, and CEROL, CREOL, the College of Optics and Photonics, University of Central Florida. He served as the head of the Laser Engineering Department at the National Institute of Laser Enhanced Sciences at Cairo University from 2022 to 2025, and also he was a research associate and the founding director of the Quantum Communication and Cryptography Lab, QCCL, at the World City of Sciences and Technology since 2025. He has been associate professor with information technology and the computer science school at Nile University. His research spans optical processing of quantum information, photonic quantum computing, practical security of quantum cryptography, quantum random number generation, quantum photonic simulator, photonic entanglement, and optical communication, optical chaos-based systems, and optical image encryption.
Assalamu alaikum. Bismillahirrahmanirrahim. It's my honor and a pleasure to be invited to this event. My talk today is about building secure quantum communication systems. So all of us know about the secrecy of quantum cryptography, but today we'll reach a further distance by talking about implementations and the quantum systems. Whenever there is implementation, we will have non-idealities and non-imperfection, and this will affect the security. This is a campus of Nile University at 6 October. So let's start by talking about photons. Why photons are our communication particles, our flying qubits? Photons are different. They are chargeless, massless, weakly interacting with each other, So they have long decoherence time, can be easily guided through atmosphere and optical fiber channels, can be delayed and manipulated using very simple optical devices existing in every lab, maybe in Egypt or any country. So quantum photonic systems, not only the quantum cryptography, but quantum photonic systems in general, can be implemented, can be readily implementable in Egypt. So let's move to one of the most important, and all of us know about it, one of the most important quantum protocols in quantum cryptography. I'll talk about BB84. Most of us knows about BB84, so we will start by talking about BB84. Then after that, we will talk that this is an ideal version of BB84. What about non-ideality of devices and how this non-ideality can be used to overcome the unconditional security we talk about. Okay, in BB84, we have Alice and Bob. Initially, in the first step, Alice prepares a random sequence of zeros and ones. Random sequence. So we need for random number generation. Okay, random number generation. Random number generation can be easily generated using a MATLAB, using C++ or any other language, but this is pseudo random number generation, and the attacker, will know very well about, maybe about, deterministically about the sequence of zeros and ones that you have generated. So we will need for some physical process to generate the sequence, the random sequence randomly. Here is a setup, and all over the presentation, we will talk about setups, how to implement this in your lab, okay? In this setup, we have single photon pulse, 50-50 beam splitter that split the photon wave function between two paths, and we have two single photon detectors, so there will be 50% probability that the first detector will be triggered, and 50% that the second detector will be triggered. If the first detector is triggered, so the BC will register 0. If the second is triggered, so the BC will register 1. So among a number of photons, we will have a very random sequence between zeros and ones. Nobody knows about which path the photon will be detected at. We are sure that the photon will be detected in only one path of them, okay? Maybe not detected at all because if we have a quantum efficiency for the detectors. But if it is detected by one of them, it will not be detected by the other, okay? So this is a physical random number generation. Nobody knows about the sequence in advance, and this is very important in security. So the first step, after the first step, Alice will use this random sequence to encode photons in some degree of freedom. Here we will have the simplest degree of freedom, the polarization of the photon. Polarization is the plane where the photon have electric field oscillations. It can be linear polarized, it can be circular polarized, it can be elliptical polarized, linear in vertical or horizontal or diagonal or anti-diagonal, okay. So Alice will encode the photon in polarization degree of freedom by zeros and ones. But not like the classical encoding. Here in quantum encoding, we will encode the photons into randomly, mutually unbiased basis. What's mutually unbiased basis? Here we have 0 and 1, plus or minus. We have two directions of polarizations, horizontal, vertical, and anti-diagonal and diagonal. Whenever any observer, Bob or anybody, detects the photon in one of the on one of these, they measure the one of in one of these bases. This will not certainly mean that Alice sent them, because it means, what about your basis? And if your basis is matched to Alice basis, there should be matching between your basis as a receiver and Alice as a sender. So we'll have encoding in 0 and basis and plus minus basis. Here we have a setup, as you see. Pulsed laser generates pulses attenuated to single photon and then controlled and rotated the polarization using the random number sequence we have just generated on our PC. So sending this encoded polarization, encoded photons to Bob through the quantum channel. Okay, Bob on his side will measure photons. He cannot measure photons in horizontal vertical basis only, or plus minus basis only. Alice randomly switching between the two bases. So Bob on his side will measure randomly in the two bases. This can be actively made by using polarization rotator, another polarization rotator on Bob's side. Another setup which is more secure and simpler actually is using passive switching between the two bases. Here we have a polarizing beam splitter. We have polarizing beam splitters, this one and this one. The first one is measuring in plus minus basis. The second one is measuring in horizontal vertical basis. Plus minus basis space is made by this polarization rotator. Whenever a photon comes to this beam splitter, it can be equally likely to detect it along this path or along this path. If it is measured here, this means that it will be measured in plus minus basis. If it was measured on the other side, it will be measured in horizontal vertical basis. Nobody knows, Bob, Alice, anybody knows which arm the photon will be detected at. This is the security here, and this is important because it is natural without any switching. So in the fourth step, Alice and Bob will check the compatibility. They both used randomly two bases. So Alice, through the channel, called Bob and tell him, hello Bob, tell me about times and the basis of your measurement. Bob, Alice, how are you? I'll send you the times that I measured the photons and at which basis I measured them. After that, Alice check the basis of Bob measurements and find the matching between the basis of Bob basis and her basis, and tell him to drop some cases where the both bases was not matched. Something like here, for example, she sent her photon as horizontal in horizontal vertical basis, but Bob measured in diagonal anti-diagonal basis, so this will be dropped. Okay, all these events will be dropped with unmatched basis, and ask him to check some results of, so for example, the fourth event, 5 event, and 6 event. If both are matched, Alice will tell him to, okay, we have a secure quantum key, and we'll have a secure channel between Alice and Bob to be used after that. What Eve can do? Eve needs to share the key initially. So first thing that anybody can think about, Eve can use cloning, for example. She may take the photon and make a clone of this photon and measure it without affecting anything. But this is prohibited by quantum mechanics, the no cloning theorem. Very rigid and very rigorous and very simple to be proved by any first class quantum mechanics persons, that quantum particle state cannot be copied perfectly. So the other thing is that she can try to intercept the photon and measure it and resend another photon with her measurement. But if Eve has the same basis of Alice and Bob, there will not be a problem. Forever, Eve, the eavesdropper, the attacker, will measure the same measurements of Alice and send to Bob. No problem and no errors in this case. But because Alice basis and the Bob basis was not announced initially, at some cases, 50%, Alice will introduce errors in 50% of the cases, 50% of 50%, this will be 25% errors. The main conclusion here that the secret key, if shared by another party, Alice and Bob will notice a high error rate. And the other main thing that we know about quantum encryption and BIP84, that quantum key distribution is unconditionally secure. The unconditional security principle means that your secrecy now is not based on the power of the intruder. If he is very powerful and have every knowledge and have very good experience, very good devices, can replace the channel, it will be ideal in this case. But these four ideal devices. For practical devices with imperfection, the security cannot be guaranteed. So let's check out some practical issues that we may face in quantum key distribution system. We will study two famous examples. One of them on the source side, okay, at Alice, and the other one at Bob on the detection side. We will introduce imperfection, practical imperfection, existing in our devices, and show how this will affect the secrecy of our key distribution. How to generate single photons? The famous method is using pulsed laser and attenuating these pulses, generating a faint pulses, which is very attenuated to a scale that we have few photons or 1 photon per pulse. This is ideal if you think that we can attenuate any pulse to reach the single photon limit. This is not accurate because we have a statistics. It's coherent states. And this coherent state is ruled by Poisson statistics. Nobody knows about the number of photons per pulse. You attenuated it, okay, you just affect the average number, the mean number of photons per pulse, which is written here as lambda. The energy of pulse divided by the energy of a single photon. Lambda is the mean number of photons, and using this attenuator, you just affected this parameter, which is the average number of photons. Okay, what about Poisson statistics? In Poisson statistics, the probability that we have number of photons n, if the mean is lambda, is ruled by this relation. P of n equal e power minus lambda multiplied by lambda power n over n factorial. Poisson statistics, for example, can be shown here in this figure. If we have lambda equal 1, for example, so you try to attenuate the pulse to the level that you have just 1 photon on average in your pulse, you will find that there will be a probability about 0.37 that you will have no photons. It will be empty pulse. Another probability identical to the first one, that you will have first one single photon, about 18% that you will have 2 photons, 3 photons, 4 photons, and so on. What is the problem in this case? The problem in this case that Eve can split the pulse, can split the number of photons and share photons with Bob without any notice. Let's check this example. If we take lambda by 0.1 here, the probability of empty pulse will be 90%, the probability of single photon pulse will be 9%, and the probability of more than 1 photon will be 1%. The problem here with this probability, the 1%, I mentioned this example because this example is used in the practical quantum key distribution system to limit the number of photons per pulse. Single photon source, not true single photon source. It's statistics, there is statistics, and there may be huge number or multiple photons per pulse that can be used for attacking. Okay, based on this loophole, this vulnerability, we will have one of the first practical attacks that affects the BB84 protocol. It's photon number splitting attack. It's called the BNS attack. BNS attack, photon number splitting attack. In this case, Alice and Bob have a practical lossy channel with 90% loss, for example. Alice send photon along that channel to Bob. This photon can be detected by Bob, but with some probability, this photon can be absorbed by channel. Here we have a probability 90% that this photon will not be detected by Bob. What Eve can do? Eve, in photon number splitting attack, typically have capabilities. She can replace the channel between Alice and Bob by a low loss channel and benefit from the difference of the loss. Eve can use quantum non-domination measurement to detect the number of photons here and then block single photon signals because she cannot share the single photon pulses. But if we have 2 photons per pulse, for example, or multiple photons, in this case, Eve can share based on the quantum non-domination measurement detecting that we have number of photons. She can share the photons with Bob, in this case, without any notice. The conclusion here that away from rigorous proofs of unconditional security over lossy channel, the key can be shared by eavesdropper without notice. This is a huge problem. We talk about a paper in 1995 after BB84 by about 11 years. And by publishing this paper, the community was shocked. This is a problem, big problem, because we thought that quantum mechanics offer ultimate security, unconditional security. There is some system for Eve to attack this security without notice. From 1995 to 2003, for something like 8 years, this problem was shocking the community, and many scientists introduced proposals to overcome this vulnerability. The one which was the simplest protocol and the most effective protocol, that this protocol, when published in Physical Review Letters in 2003, this protocol actually deleted anything related to the photon number splitting attack, is the decoy state protocol. In decoy state protocol, Alice have a source that generates single photon pulse. This is okay, but in some cases, and intentionally, Alice will increase the number of photons average per pulse, above 0.1, for example. Instead of 0.1 photon per second, we will have something like an average 2 photons per second, for example. And after that, Alice and Bob will measure the loss percentage in the first case of single photon pulses and in the second case of multiple photon pulses. If Eve was not launching the photon number splitting attack, X percentage and Y percentage will be the same. This is passive channel, and X percentage and Y percentage should be the same. If we have Y percentage higher than, or for the loss lower than X percentage, so we will have photon number splitting attack and the protocol will be aborted. The decoy-state protocol, very simple protocol so far until now, well used within the practical quantum key distribution systems. Okay, this is the first loophole on the source side. Let's move to the second loophole on the detection side. I'll skip about the physics in the single photon detector and how the single photon avalanche photon detector detect the photons, but let's just know about this diagram here. We have single photon pulses, okay, and this is a single photon source with 2 channels or 2 ports. The optical port that detect from it, it's interact with single photons, and we have electrical port to generate TTL pulses, electrical pulses, something like voltage, up to 5 volts and with width something like 20 nanosecond. Ideally, the single photon detector just detects single photon pulses with some efficiency. But in another attack called detector control attack, Eve can illuminate the detector, the single photon detector, by blinding light. Blinding light will change the operation of the single photon detector from the Geiger mode to the linear mode. In this case, the single photon detector will not be sensitive to single photon. Eve will measure the single photons come from Alice and then generate bright pulses like this to trigger the detector on Bob's side. If the bright pulse is above some threshold, it will be counted. If under some threshold, it will not be counted. How this can be used to remote control the detectors of Bob? If Eve adjusted the level of the trigger pulse to be just above the threshold, in this case, if Eve has the same basis of Bob basis, the whole pulse will be go to single detector. It is above the threshold and going to single detector, there will be a clack. What if Bob have another or have the other basis? In this case, for example, Eve sending on horizontal vertical basis and Bob measuring on diagonal and diagonal basis. In this case, the energy will be split between the two detectors. Okay, by splitting this huge pulse, this smaller pulse will be less than the threshold. And in this case, no clicks will happen because we are under threshold. So this can be used to remote controlling the detectors at Bob's side without notice. It's different from the photon number splitting attack. Photon number splitting attack, as we said, was killed in 2003 by launching the decoy state protocol. But so far, we have a vulnerability in the detector control attack. Okay. For this attack, we have introduced a practical way to overcome detector control attack. This system, as you see here, we have on the gateway, we have a randomizer, polarization randomizer, and a state converter. The state converter operating in the optical domain, it converts between path and the polarization and time band. Translate the polarization to time band in one direction and translate back the time band to polarization in the other direction. The same thing for the path. So let's review the steps of this quantum key distribution system process. Initially, we have an initial state, psi1. Psi1, here as we wrote it, it's in polarization and the path. So we have a photon in diagonal polarization in path A. So we are in path A here, and this laser injects a photon of diagonal polarization through the polarizing beam splitter. The horizontal polarization will go through the longer arm, and the vertical polarization will reflect on the shorter arm. So H will turn to T long, and V will be translated to T short. In this case, we have this state converter actually moving or translating the polarization degree of freedom qubit into time band qubit. Also, the vertical polarization here will be translated into horizontal polarization using this polarization controller on the shorter arm. So A will be changed to H. After that, going through the optical fiber channel to Alice and the Faraday mirror. This FM or Faraday mirror is not a traditional mirror. What is the difference between Faraday mirror and the mirror, the traditional mirror? Faraday mirror will reflect the photon. The photon will have orthogonal polarization, orthogonal to the input polarization. So in this case, we'll have, instead of horizontal polarization, we have a vertical polarization. We have still the time band, and Alice encoded the photon by a phase phi A. Through the state converter, we will transfer back the time band state, T long and T short, to H and V, and the vertical polarization will be translated into B in this case. So all photons going from Bob to Alice will return back through the secure arm here and will be detected by the detectors on the secure path. What if Eve intercepts the photon? So the photon will go to Alice and return back to Eve. Eve will intercept the photon in case of attack and measure it and generate another photon with these mixed states, general state, going through the state converter. Sorry about this. Is something like compatibility issue between the Mac and the Windows here. But we have here a state for the photon after the polarizing beam splitter. I hope the second one will be good. Okay. So let's move to the PDF. It will be better. So here we have the state of the photon after reaching the polarizing beam splitter. And then we will trace over the polarization. We have this spatial state. As we see, there is a probability for Eve photon to be detected in the alert path. This is a problem for Eve because all photons generated by Eve cannot actually pass this test because there will be always a probability for the photon to be detected in the alert path, and we have actually calculated it in this form. So we have probability for Eve, we have BA, probability that photon will be detected in the alert path, and the BB, that the photon will be detected in the secure path. Okay, if we have number of photons like detector control attack, if we have number of photons, this probability will affect the energy of the photons detected on the alert path and the other energy in the secure path. We have EA and EB, the energy detected at alert and the alert path, and EB in the secure path. We relied on the click probability for one of the commercial products, detector products, single photon products for ID Quantique. This is one's experimental measurement here for the click probability versus the trigger pulse energy. We model or approximate this click probability by ramp step function to complete the calculations, and we could calculate the alert rate through this form and the shifted key rate. The alert rate is the rate that detector control attack will trigger photons on the alert, trigger detector on the alert path. And the shifted key rate is the rate that photons will be triggering the secure path detectors. Under some assumptions which are realistic, we could have the shifted key and the alert key here. In this figure, we have the shifted key rate after detector control attack in green, and the alert rate in red. As you see, for different values of blinding power, we have forever the alert rate is higher than the shifted key rate. So whenever Eve generate detector control or launch a detector control attack, the alert rate will be higher than the shifted key rate. Our lab, Quantum Communications and Cryptography lab, established in 2023. We have established quantum random number generator in this lab, FPGA-based coincidence measurement, and quantum photonic simulator and single photon source. And under construction, we have the quantum key distribution system. This is a group of researchers. We have here Ahmed and the lab equipments. This quantum random number generator, we have established it in our lab. It's FPGA and connected by single photon detectors and connected via Ethernet to a laptop. And we could generate random sequence which is physically random at a rate about 28 megabit per second, physical random sequences. And we also constructed coincidence detection measurement based on the FPGA and the LabVIEW. And faint pulse single photon source. We also worked on quantum photonic simulators. This is a version 1, and we have version 2, totally Python, and you can just line by line introduce something like you have phase shifter, beam splitter, and some input state, and you will have the unitary gate that describes this optical setup and the probability of the photon to be measured on any of these passes. So the conclusion, despite quantum key distribution is unconditionally secure for ideal systems, but for some imperfections, we have vulnerabilities. We have introduced a quantum key distribution system that produces count rate on the alert detector for any state generated by Eve. These some publications related to our quantum key distribution system in GLT and in QCrypt and in Caleo, and we have a US patent in the last year. Thank you.
Thanks, Dr. Salim, for the nice presentation and the great work. Please, does anyone have a question? Yes.
I have there's something in the circuit just I wanted to ask about, like 5-6 slides back, if you can show it, please.
Okay. Which slide?
Like towards the end. Yeah, more up. Again. Yes. Here. The loops in the circuit, like the one labeled PC, and like what does these loops do?
BMZI?
Like PC and like
polarization controller.
What does the loops do? Like what are their functions?
Thanks for your question. Okay, so you are asking about the polarization controller. Its function is as written here. Polarization controller is just a rotator, polarization rotator, okay? But it works on the optical fiber connections, okay? So we have a polarization rotator, an optical fiber that transfer horizontal to vertical photons or vertical to horizontal, okay? Something like quantum not gate. Quantum not gate. It's just moving between 0 and 1, and if you have 0, you will have 1. If 1, 0. Alpha 0 plus beta 1, alpha 1 plus beta 0, and so on. Okay.
Okay. So for the time, then we are gonna stop here. We would like to thank Dr. Salim for the great presentation and this wonderful effort that has been highlighted. And feel free to ask him during the coffee break and the lunch. Thanks again, Dr. Salim.
Thank you so much. Thank you so much.